At 4,000 meters, about 13,120 feet, the ocean doesn't just look different. It forces life to run on different rules. And that's why deep-sea animals can seem so strange. But here's the detail most people miss. Depth doesn't take warmth first. It takes reliable light. And once light collapses, everything, how animals hide, hunt, and even shape their bodies, starts changing. In this episode, we're going to do something simple. We'll build a model you can reuse anytime you see deep-sea footage go viral. 4 forces explain most of what you're seeing: light, pressure, food, and oxygen. So what happens when the sun finally disappears? Before we go deeper, we need a quick map of what depth really means. The ocean isn't one uniform space, it's layered. The first major shift begins around 200 meters or 656 feet. That's often called the twilight zone. There's still light, but it's weak and inconsistent. Shapes fade, colors lose meaning, and visibility becomes a problem you can't solve with blending in. By around 1,000 meters or 3,280 feet, you've entered the midnight zone, where sunlight is essentially gone. And from there down to 4,000 meters or 13,120 feet, the world becomes steadily darker, colder, and more demanding. Now here's the big idea. Depth changes several things in predictable ways, especially light, pressure, oxygen, and food. Some changes are gradual. Some happen in layers. But together, they explain why deep-sea life looks so unfamiliar. And once these constraints stack, evolution doesn't add small upgrades. It redesigns the entire strategy. So let's start with the first constraint that breaks: light. At the surface, sunlight is the default. It powers photosynthesis. It creates day and night. It gives animals a background to hide against. But as you descend, light doesn't just fade, it becomes unreliable. And that changes what it even means to see. In the twilight zone, around 200 meters or 656 feet, contrast matters more than detail. You might expect life to simply become harder to spot. Instead, something more interesting happens. Many animals shift from being colorful to being engineered around silhouettes, reflections, and shadows. In dim light, the most dangerous thing isn't a predator you can clearly see. It's a shape you barely detect. That's why you find strategies like oversized eyes, reflective tissues, and even transparent bodies in mid-water ecosystems. Not because they look weird, because they solve a lighting problem. And then, as you approach 1,000 meters or 3,280 feet, sunlight stops being useful altogether. There's no scenery, no reef, no background, just darkness. You'd think vision would stop mattering. But the deep doesn't eliminate sight. It changes what sight is used for. Instead of tracking a landscape, animals track signals, tiny movements, and most importantly, brief points of light. Because the ocean doesn't stay dark in the way most people imagine. It lights itself up. Bioluminescence, light produced by living organisms, is widespread in the midwater and deep sea. And it isn't one trick. It's a toolbox. In different animals, light can be a lure, a warning, a distraction, or camouflage. Here's the catch. In the twilight zone, light isn't only something you see. It's something you have to survive. One of the most elegant strategies here is counter-illumination. Some animals produce light on their underside to match the faint downwelling light from above. The goal is to erase their silhouette. From below, a predator shouldn't see a dark shape against a slightly brighter background. It should see nothing. Bioluminescence can also work as misdirection. Some animals shed glowing material like a decoy. Some flash to startle. Some use patterns to find mates in a world where distance visibility is terrible. So even when the ocean looks empty, it can be full of brief signals, like a city seen from far away at night. Now zoom out, because this is where the deep ocean becomes even stranger. A huge amount of life isn't parked at one depth. Every day, one of the largest migrations on Earth happens inside the water column. A dense band of animals rises toward the surface at night and sinks deeper during the day. This is the deep scattering layer, and the movement is called vertical migration. It's so massive that sonar often detects it as a moving layer. Quick reset. When sunlight fades, life doesn't quit. It turns light into signals. But if the mid-water is this active, why do deep-sea bodies still look so extreme? Because once you go deeper, the ocean stops asking, "Can you see?" It starts asking something harsher. Can your body function down here? Now we hit the constraint you can't outsmart with camouflage: pressure. A simple rule of thumb is that pressure increases by about 1 atmosphere every 10 meters, or about 1 atmosphere every 33 feet. At 4,000 meters, or 13,120 feet, that's roughly 400 atmospheres of pressure. This doesn't just make the ocean heavy. It sets mechanical limits on what bodies can safely contain and how they can stay afloat. And here's the key detail. Pressure punishes gas-filled spaces because gases compress. Near the surface, many animals use gas-filled spaces for buoyancy. Deeper down, that strategy becomes complicated and costly. So deep-sea life often relies on other approaches: oils, low-density tissues, and bodies that are more water-like in composition. This is why the deep sea can look backwards. You might expect extreme conditions to produce creatures that look tougher, more armored, more rigid. But in many deep environments, soft can be efficient. Gelatinous or lightly structured bodies can reduce energy costs, help with neutral buoyancy, and match an ecosystem where constant speed and muscle power aren't always worth the fuel. Pressure also shapes life at a smaller scale. Membranes, proteins, and internal chemistry still have to function, just under forces that don't exist near the surface. That's one reason deep-sea species can be highly specialized for a narrow range of conditions. Quick reset. Light explains the signals. Pressure explains the body plans. Now we reach the constraint that controls almost everything after that. Food. If pressure decides what your body can be, food decides what your body can afford to be. In the deep ocean, the menu is unreliable. There isn't a steady supply of prey like you'd find in sunlit waters. Much of the deep sea runs on a slow, constant drizzle of organic particles called marine snow, tiny fragments of dead plankton, waste, and debris drifting down from above. It isn't dramatic, but it's baseline fuel. And then there are rare windfalls. A dead animal sinking from the surface, especially something large, can become a temporary oasis. These food falls can feed communities for long periods, turning scarcity into sudden opportunity. Here's the catch. When meals are rare, the biggest advantage isn't speed. It's readiness. That's why deep-sea animals often look overbuilt in the places you'd least expect. Large mouths, big jaws, teeth that look exaggerated for the body size. You'd think a predator in the deep would need to chase, but chasing can be a waste of energy. If you only get a few real chances to eat, evolution favors designs that maximize success when the moment finally arrives. This is also why so many deep-sea lifestyles feel slow. Waiting can beat searching. Opportunism can beat aggression. Efficiency can beat speed. So a lot of what looks monstrous is really probability management, built for darkness, built for pressure, and built for rare opportunities. But there's still a complication. Because even in the same darkness, not every region of the ocean has the same oxygen, and that changes who can live where. So far, our model sounds clean: less light, more pressure, less food, stranger designs. But the deep ocean isn't one uniform blueprint. Oxygen minimum zones, or OMZs, are regions where dissolved oxygen drops dramatically at certain depths. These zones can act like invisible walls, reshaping where animals can live and how active they can be. At the same time, away from hydrothermal vents, much of the deep ocean stays cold, often around 0 to 4 degrees Celsius, or 32 to 39 degrees Fahrenheit. Cold water can hold more dissolved oxygen than warm water. That sounds like it should make life easier. But OMZs can still create low oxygen bottlenecks. And in those layers, the balance between oxygen supply and energy demand becomes critical. This is where deep-sea gigantism enters the conversation. Yes, some deep-sea groups do tend to grow larger than their shallow water relatives, but it isn't a universal rule, and it doesn't happen the same way everywhere. It depends on temperature, oxygen, and food interacting at once. So instead of depth makes everything huge, the evidence supports something more careful. Depth can shift limits, but the local environment decides which direction evolution can afford to go. Oxygen also helps explain why two regions can be equally dark, yet the animals differ because oxygen and chemistry are not the same. And there's one exception worth remembering. Not all deep-sea life depends on food falling from above. Hydrothermal vents and cold seeps can support ecosystems powered by chemosynthesis, microbes using chemical energy instead of sunlight. These sites aren't everywhere, but where they exist, they can flip local scarcity and create hotspots of life in the darkness. Now we can do what most videos skip. We can separate what's confirmed, what's likely, and what's still uncertain, and rank the drivers in a way that stays inside the evidence. Here's what we know. Depth predictably changes light, pressure, oxygen, and food. Below about 1,000 meters or 3,280 feet, sunlight is essentially gone. Pressure becomes a constant constraint, and food becomes less reliable. Here's what we don't fully know. We still can't say exactly how many deep-sea species exist because a lot of biodiversity remains undescribed. Many behaviors are inferred from limited footage, and large parts of the seafloor still aren't mapped at.